So good morning. It's a pleasure this morning to welcome Michael Coughlin. Michael prepared his PhD at Harvard University. He's now a postdoc at Caltech. Among several things, he's an expert in the search for transient, and especially transient associated with gravitational waves. He's member of several collaborations looking for transient with standard observational astronomy like the ZTF, LSST, PanSTARRS, and is also a member of LIGO. And this is, of course, in a very interesting position at that moment since the first discovery of a binary neutron-star merger and associated electromagnetic counterpart. And this is probably the topic of today. So thank you very much.
Okay. Can everyone hear me? Is this on? Okay. All right. So thank you for the introduction and thank you for the invitation. I know that you have all heard a lot of talks about 1708-17, and so my plan for today is to not talk much about LIGO or talk much about specifically about the binary neutron star, but some of the work that we're doing from the past gravitational wave searches and sort of looking forward to the future about what we might expect to be doing and how we can expect or hope to do it a little bit better than we did for the case of 1708-17. But I would be kind of remiss if I didn't mention this briefly. So I really like this, the cartoon, because we have Fermi here detecting 1708-17, and then in this case, this is an image of the Blanco telescope with the dark energy camera down in Chile detecting the Kilonovae. And I kind of laugh at this one because here's David Shoemaker, the head of LIGO or the spokesperson of LIGO, who is laughing or disappointed because when Hubble, the name of the image, when it took the image of 1708-17, it had BNS merger in the name, and so everyone knew about this. It was, of course, an open secret. But I just want to say, so my hope for this talk is to talk a little bit about what we can take away from 1708-17 in order to do a better job searching for the counterpart as well as interpreting the event when we have hopefully a handful of events going forwards. So for those of you who don't know, this is the way I like to think about how we do gravitational wave counterpart searches. And so there are two major ways that this was done in 1708-17. So the first is where you have these wide field of view surveys. So these include PanSTARRS and Atlas, which I'll talk about, which are in Hawaii, the dark energy camera in Chile, and eventually LSST, which will also be in Chile. And so the way that these generally work is these are survey instruments, and so nominally they're taking images of either most of the sky available to them at any given time, and they generate reference images to do image differencing. But basically the way they work is you take the sky maps as returned by LIGO or predicted by the Fermi satellite or what have you, and you make tiles of the sky and you go point and look for counterparts that way. Now the other way that was also very successful for 1708-17 is what's known as galaxy targeted follow-ups. And so the way that this works is quite different, where instead of just tiling the entire region and trying to find the counterpart, you take known galaxies and point your telescope at those galaxies and look for new objects. And so both of these methods were very successful for 1708-17. I think half the teams that found it was using one and half the teams that found it was using the other. And we'll talk just very briefly about how we're thinking about combining the power of some of these for ZTF, for example. But onwards, so if you have your wide field of view survey or galaxy targeted follow-up, you generate a list of candidates. And of course, for a survey like ZTF or any of these are constantly finding transients, either supernovae or CVs or kind of anything that is variable on the sky. And so you have to figure out a way to go from I have a lot of potential counterparts to my gravitational wave event. How do I go about doing that? And so there are two major ways of doing so. One, you get further photometry, as in you take more images of the list of candidates that you have on hand, or in addition, you get spectra, as in you do spectroscopy on these objects. And hopefully with a combination of the two, by understanding properties from models or by combining these two together, you can think about identifying which was the true object. And so in the 1708-17 case, it was a combination of both. There was a lot of photometry and a lot of spectra. But of course, in future events, as we don't expect to use all of the telescopes in the world, essentially, to follow up these events, hopefully we can think about being a little smarter about how to use photometry and spectra to rapidly identify the objects. And finally, once you've identified it, you use these same techniques to characterize it and learn about the equation of state of neutron stars or the various other physics that were done with 1708-17. Okay, so that's sort of a rapid overview of how these counterpart searches work. But I'm going to talk just a little bit specifically about some work we did during the last few science runs with PanSTARRS and Atlas. So PanSTARRS is so on the right here is what's known as PanSTARRS 1, and on the left is PanSTARRS 2. And so there's actually going to be two telescopes operating going forward. But it's about 7 square degree field imager on Haleakala in Hawaii. And just like ZTF for dark energy camera, it's a survey that's surveying the entire sky visible from Hawaii every 3 or 4 nights or so due to the size of its field of view. And very similarly, the same people who are doing the PanSTARRS survey are working on Atlas, which is a NASA-funded telescope with a much wider field of view, kind of 50 square degrees, so very, very large. That isn't quite as large. It's like it's a sub-meter telescope. But what's cool about this one is there's another telescope on another island in Hawaii, and so between those two, it actually images the whole sky, or maybe a little bit more often, actually, every night. And so it's instruments like this that are one of the very useful tools for doing these searches, because not only do they have these really wide field of view cameras so as to be able to cover like 1,000 square degrees like you get with LIGO sometimes, but also since they're observing the sky so often, we often know what transients are new and what are not. Okay, so here I list 4 of the released events that have been published by LIGO and were followed up by both PanSTARRS and Atlas. And I think what I want to mostly highlight here is that there's an opportunity for telescopes of this type to do what are known as target of opportunity observations, of course, as in if a gravitational wave or a short gamma-ray burst or what have you comes through, we can turn and we can break the survey mode and actually go ahead and image the sky map. But what's kind of cool about some of these others is that, and again, sort of looking forward, is that we're able to do some of them in what's in the nominal survey mode. So Atlas is supposed to be looking for near-Earth objects, as in asteroids. But we were actually able to, just without breaking the cadence, we were able to do a not insignificant part of the 1708-14 region, or at least the part in the north that was available to us. And so looking forward, one of the things that I'm most excited about actually is what will be the benefits of these wide field of view instruments such as LSST without having to break off cadence and do specific gravitational wave searches with them. Let's see. Okay, so to give you a feel for what we were actually up to, so I'm sure everyone here has seen what these localization regions from the gravitational wave detectors look like. So they make these big rings on the sky due to the beam patterns of Hanford and Livingston and Virgo when it's on. But one of the cool things was since PanSTARRS and Atlas, since they're the same teams, there was some amount of coordination that could actually go on when we were looking for these gravitational wave counterparts. And so our general strategy, without having thought about it too much, was broadly, we have in green here these these circles, and they're overlapping, and so you can't really see that much about what's going on. But broadly, PanSTARRS, we'd have image sort of the inner 50% or so of these localization regions. And PanSTARRS is nice because it goes a little bit deeper than Atlas does. It's a bigger telescope and a smaller imager, so its sensitivity is a little bit better. And so we had it really dig deep kind of in the inner regions. And then with Atlas, with this 50 square degree square imager in purple here, we were able to do sort of cover the rest of the region that was available from the north. And most of these were set by the time we could do them. But basically, we had sort of this top hat strategy where we'd have one telescope doing sort of the inner part and one doing the rest as best it could. And so what this led to, if I was to try to say, so for most of these events that we did, they were binary black holes. And so, and a number of papers have been written about, are there electromagnetic counterparts to black holes? But more likely, of course, is that we're not going to detect anything. And so for these binary black hole searches with these surveys, what was really more going on was that we were essentially practicing for what would eventually be the BNS. And so it cuts off just a little bit on the screen here, but what you have on the x-axis is distance, and down here is about 100 megaparsecs. And then on the y-axis is we have detection efficiency. So this is a very sort of gravitational wave-esque way of characterizing how good am I at doing the search that I want to do, as in what percentage of potential counterparts in this case that are consistent with 170817. So this is one way that we use 170817 is we were able to go back and when we were doing our searches and say, if this had been a binary neutron star with this localization region at some distance, how likely would we have been to actually detect it with the strategy that we had? And so what we have here is sort of this bimodal thing, or these top hats. And so what you have is that the higher detection efficiencies, or the place that's higher but to a lower distance, this is due to Atlas's contribution, the fact that it was able to go wider but a little bit shallower than the surveys. And then you get a little bump here and a little bump here from the fact that PanSTARRS, while doing that same region, or a smaller part of that region, did go a bit deeper, and so could actually go out to a few hundred megaparsecs. And so this was one way that we were able to sort of coordinate to some degree the contribution of pretty complementary telescopes and give sort of an idea for how one might do this in the future.
Quick question, you're using the broad filter on PanSTARRS, or what is it you're using?
Yeah. So we used both cyan and orange. Cyan is this sort of RG thing, and orange is kind of R&I-ish. But yes, we were using whatever filter was actually in there, we would just tile the sky with. Yeah, so that depends on the amount of time that we were willing to follow up with. So, what we learned from 170817, of course, was that we had this blue part that faded relatively quickly, and then a red part that was a little slower. Due to the fact that 170817 was quite bright, it wouldn't have really mattered. But we've been thinking a little bit about, for example, if you have multiple telescopes, what are the appropriate filter combinations that you might think about using? But in this case, it was not something we bothered with. Okay, so just finally, in terms of some things that you can think about and what this teaches us for future surveys. So this blue band here corresponds to the range of BNS rates that LIGO gives us. And if you assume that all BNS mergers give the same Kilonova counterpart as one another, which we're pretty sure that they don't, but this was to essentially give an idea in various survey modes. So for example, Atlas with one telescope, Atlas with two telescopes, PanSTARRS, LSST. What are the number of optical counterparts that you'd expect to detect serendipitously? As in, if I was to just do the normal survey mode, how many of them would I find? And so the answer is actually not that many. And so this is number of optical counterparts per year. And you'll see on this axis that one crosses right here. So depending on the instrument you have, for example, LSST, which will be the best. It is only of order 1, and perhaps, and that's even at a relatively generous rate, and assuming that all of these objects end up with kilonova counterparts. And so one takeaway from this is that our TOOs, or mapping these sky maps, will continue to be an important part, even when we have these 8-meter class surveys.
So this is to detect one-point photometry?
This is two. So I asked for 2 detections, 1 day apart, and no difference in colors. So it was a very generous, it was very conservative, I guess I should say, as in like, this is by far the best one could imagine doing, and we'll probably do a lot worse. Yes? Yes?
You're going to explain how it works, because I mean, you've got a tons of transients, you're going to explain that?
Yeah, so...
What's the signature to do?
Yeah, so I should say, this is me just saying, what is the best we could possibly do? I'm not saying that we're going to be able to, I'm essentially arguing that this is going to be really hard to do. If the rate at best is only about 1 per year, then this is not something that we're going to be expecting to be able to do very well, right? Okay. Okay. So we're going to switch gears to a little bit to what we're doing now. And so I was part of the PanSTARRS and Atlas teams during 01 and 02, and now I'm at Caltech, and so I joined ZTF. And the strategy here is a little bit different. So the P48, this is this 48-inch telescope on Palomar. This is where ZTF, this big 47-ish square degree camera, lives. And it images the sky visible to it every couple nights or so. But the thing that's cool about working with ZTF or at Caltech is that there are other telescopes on this mountain. And so the broad strategy has been, we have ZTF here, and on the 60-inch over here, we have what's known as the SED machine. But basically, it's this robotic spectrograph. And we found this to be very useful for rapidly classifying transients that ZTF finds. And then finally, we have the big 200-inch, which also has a spectrograph on it. Okay, so with ZTF, you can see an image of the camera here. It's got a bunch of quadrants and the like. As a pathfinder, so ZTF was sort of being commissioned right around the time that 1708-17 happened. And so it was actually kind of an unfortunate timing for that camera. But as sort of a pathfinder to what's going to happen during 03, is we've been doing short GRB follow-ups from Fermi. And so the reason I'm going to highlight this event is as follows. So here you have the 50% region, here you have the 90% region. It looks quite a bit different than what these LIGO sky maps look like, but in principle the search strategies are quite similar. And this was about something like a 4,000-ish square degree field that nominally, if we wanted to do all 90%, it was something like that. And so with ZTF, we chose to cover something a little bit more reasonable, about 2,900 square degrees, and got up to about 60%, 62% of this region. And so while the probability doesn't sound that high, to some degree, going to a depth of about 20 and a half or 21 is relatively unprecedented to cover literally thousands of square degrees. And we'll show in a second how we were able to whittle down candidates and actually show that at least within the region we covered, we didn't detect any afterglows. So just sort of to bring us back to where we are, we're at a stage where we have all of our candidates and how to do the photometry and identification part. And so one of the main benefits of the way that the survey is done is what's this SED machine on the 60-inch. And so what this is, it's both an imager and integral field unit spectrograph. So in here, in the middle here, you have this spectrograph, which is, it has like an R of 100 or so, so it's relatively coarse, but what we found is that it's been good enough for simply classifying objects. And so if you want to get high resolution spectra, you can go to the 200-inch or elsewhere, but broadly its purpose is to simply classify transients. And then in addition, it has these 4 imager parts with 4 different filters. And so with this GRB, after having covered 2,900 square degrees, one of the great things about working on ZTF or one of these survey instruments is the fact that, as most of you know, if you were to cover thousands of square degrees and not have any idea about what was happening in the sky, you'd find a lot of new stuff. And so the fact that we had imaging as of the night or a few nights before in most of the fields we covered, it meant we whittled down from potentially hundreds of new objects to just 14. And this was done using a relatively very, very loose criteria, as in we weren't doing color cuts or anything else, because we're trying to not claim that we know everything about the counterparts we're looking for, but broadly we check. Is there a known variable star, or is there a known asteroid? We have our machine learning algorithms that provide some amount of cut, but it's relatively conservative. We stay away from the bright stars, as in with all the blooming and the like, and of course we check that it's actually within the fields that we care about. And so this resulted in just 14 objects, and we quote R of 20.3 here, and it was like 20.6 or something. But with the fact that the fields were setting and the like, we were actually able to get spectra or further photometry of most of them. And with both of those, we were able to basically check that they weren't the afterglows that we were looking for. And so SEDM, for example, gives very coarse spectra like this. And broadly, what we found is that the 14 new objects were either new supernovae or AGN, and we handed those off to the relevant ZTF groups. And I think that's worth a mention for a moment. Since one of the big concerns about the TOOs with these big surveys is the fact that we are taking away time from what is nominally, depending on your point of view in ZTF, a supernovae survey or whatever other science that people are interested in. And so one of the cool things is it wasn't a waste of time. We were able to provide new young supernovae to the supernovae group and the like. And so it was sort of a boon for them while using a relatively limited amount of time. We spend around 3 hours or so with ZTF on any given GRB. And so it hasn't been a big time investment for doing relatively decent coverage for these GRBs. So the question does come up, how many of these afterglows are you expecting to actually see? And so our strategy so far has been, ZTF's nominal cadence is a 30-second image. And so with these GRBs, due to the fact that ZTF does not have a guider on it, and so we can't do really, really long exposures like you might like to do with these telescopes, we've been doing about 3-ish minute exposures, and that's been getting us close-ish to about 20 seconds. And so you can see from this plot here, so in the green band I covered sort of the time window and the apparent magnitude limits that we were able to place. And for this object in particular, it occurred during the daytime at Palomar, and so it took us a number of hours to get on the sky and the like, but very similar to the gravitational wave case, really. But we do cross some of the known, these are just plotting known afterglows. And so we're able to get at least some part of the interesting parameter space, and hope it'll be enough to get future afterglows. So of course there are some sort of technical challenges associated with it, both technical and observational challenges. And so on the bottom plot here, we have time versus quote unquote number of successful quadrants passed. And so there are 64 quadrants in the ZTF camera. It's not just one chip, it's a bunch of chips. And so the way that the processing is done is such that in any given quadrant, you check things like, was the atmosphere making it such that the point spread function of the objects we were looking at, did it pass some quality cut? And you can see that, for example, on the first night on May 24th, at least early in the night, there was a lot of quadrants that failed this cut. And so basically, the point is that there are still, even with these wide field imagers, observational challenges in terms of when I say that we were on the sky within 5 hours, there is still, even so, in practice, we lost half of those images essentially in the early part of the night, and so there's only so much benefit we can gain from that. On the other hand, on the second night, the weather was much better, and so we had all of the images we took were actually useful. But the point of this is that even with imagers like this, we don't get all of the benefit we should. So, as sort of a summary, so far we've done 4 GRBs, and we have not detected any counterparts for any of them so far. So this is the first one I talked about, the 60%. We have done a pair that with kind of smaller localization regions to cover, and so we've covered about 90% of both of those. And the reason we're at this 90% number as opposed to 100 is that one of the blessings and the curses of ZTF, for example, is the fact that instead of being able to point wherever one likes, instead it uses what's known as a fixed grid. And so when it does its survey, it will go to the same point on the sky over and over again. And the reason for this is that you can more easily build what are known as reference images, or basically images that you stack together in order to compare with future images that you take to then find transients with. And so due to the way this grid is constructed, there are gaps between the chips in ZTF. And so that corresponds to about a 10% loss, and that's where this comes from. And so one of the potentially frustrating things is that with ZTF, it's always possible that the transient that you care about will fall into one of these gaps, and so that's just sort of one of the downsides. And finally, this number is relatively low because we had a GRB that was localized to the North Pole, essentially, and so at the pole, ZTF does not do above 80 degrees or below minus 30 or so, and so we actually couldn't do most of this localization region. So there's sort of this, a handful of observational and technical challenges that mean that the coverage isn't as good as one might like. But overall, I think mostly good things are happening. So I briefly highlighted the SEDM machine. But I would like to take a second to highlight another project that is also doing very similar stuff. And so for context, in addition to the telescopes on Palomar, Caltech has essentially rented out the 84-inch at Kitt Peak for the last handful of years. And so beforehand on the system, what was this adaptive optics system known as RoboAO. And in the last few months, this adaptive optics system has moved to Hawaii. And so we put a new imager on the Kitt Peak 84-inch. And it's very simple. It's got a filter wheel. It's got one of these, what are known as EMCCDs, which allow to do kind of high cadence photometry. But broadly, we now have this dedicated 84-inch telescope with a high-speed photometer that's doing some GRB follow-up, as well as eclipsing white dwarf binaries. And so this is kind of just a brief aside to my talk, so please just bear with me. So one of as I said at the start of the talk, we're talking about gravitational wave sources. So that's both for the LIGO cases in these coalescing neutron stars or neutron star black holes, but for space-based gravitational wave detectors such as LISA, we're also interested in characterizing future LISA sources. And for example, these white dwarf binaries. And so people, when they give LISA talks, talk all about how these binary white dwarfs are going to be kind of a foreground noise for basically everything else that LISA wants to see. And so one of the things that we're doing is with ZTF is because ZTF is taking data in the same spot every night, or maybe and in some fields more than once a night. If you run an algorithm designed to find periods in variable objects, you can actually, despite the fact that ZTF's only taking a handful of images a night, you can see periodicity in ZTF objects at the kind of handful of minute level. And so, which I found to be quite surprising actually. So the idea is that if you phase fold properly, or basically you stack the images properly, you can actually see that you can get some very rapid variations in the photometry over many, many months of data. And so one thing that we're doing with this 84-inch system is we're looking at ZTF finds an object that might be variable or even perhaps has an eclipse, which is exciting because that means it's probably a binary. And we're looking at we're looking for these white dwarfs. And so this is just one example of, we found about a 7-minute period binary, which is the second shortest known object like this. And so what you have here is you see that I've stacked the images in the 84-inch such that we start here at the peak brightness, and then one of the white dwarfs is going behind the other, and then finally you get this eclipse where you have essentially no flux. And the reason that we're using the Kitt Peak instrument is because we have this high-speed photometer, this EMCCD, and we're able to tune up the gain such that we can actually try to explore what's happening right at the eclipse. In a different way to look at the same plot, this is also where we've phase folded all sorts of data for the 7-minute binary. And so here what you can see is you see the eclipse coming in, and we've taken observations on other telescopes that you actually get this secondary eclipse where the other white dwarf's in front of this one. But basically you get very nice clean photometry like this. In the ZTF case, you can sort of broadly make out that there might be a 7-minute period. And so the idea is ZTF is useful for kind of creating potential targets for telescopes like this. And then you can actually go look for LISA sources and other things. So the reason that this is cool, or we think this is cool, so here is the characteristic strain as a function of frequency. So this is like every LIGO and LISA plot you essentially have ever seen. So in black is the LISA sensitivity curve. And plotted on here is the characteristic strain of the known binary systems. There's a 20-minute system that was discovered by PTF. But here, one of the cool things with this 7-minute binary is due to the period. As of now, it might be the brightest known LISA source. And so our hope is going forward, we'll be able to use a combination of ZTF and telescopes like the 84-inch to make a catalog of binaries for LISA, such that we actually know what LISA will see when it turns on. Okay, so switching back, I want to talk a little bit about how things that we're doing to improve how we actually schedule gravitational wave or short gamma-ray burst observations with these wide field of view telescopes. For those of you who don't work on this, the idea is as follows. So there are servers from LIGO or from Fermi that provide essentially sky maps, and in the gravitational wave case you also have sky maps that have distance parts, so you know how far LIGO thinks it is. And then of course you have your telescope, either ZTF or PanSTARRS or what have you, that has a specific field of view and a limiting magnitude and exposure times and how fast does it slew across the sky. So kind of what makes a telescope a telescope. So combining these two together, you create tilings, as in I want to point at region A, B, and C at these points with this particular telescope. And then once you have your tiling, you say, okay, and now I want to take 30-second exposures, 60-second exposures, or so on and so forth. And finally, once you have that, then you create a schedule for your observations, as in if I have a field that's going to set early in the night, then I want to take early. And so figuring out how to balance sort of the, can I observe everything I want to? If not, how do I actually properly prioritize this? And finally, as I've shown in other plots, once we've done all this, we'd like to assess, how well did we do with the schedule we created, as in how many potential counterparts am I likely to have seen if I'm actually to execute this queue. So this is an example of, in this case, I think it's Ellis's T. But basically, if you were to, this is what I mean by this fixed grid pattern. Basically, you have these kind of rows of potential points on the sky that you actually observe with your telescope. And so to some degree, this makes it really easy. I'm not given many options in terms of where I want to point. I'll essentially point at the tilings that fall in the window here. On the other hand, if you have a telescope like PanSTARRS or Atlas, where you don't build reference images in these same ways, you can do kind of tricks like running Monte Carlos to maximize the probability and create some amount of overlap between your tiles. And so we've been thinking about this for both kinds of telescopes. Now, we've also been doing things like testing scheduling algorithms, as in there are different ways to how we think about prioritizing fields of different probabilities. And so here's 3 different scheduling algorithms, and you can see that one, for some of them, they do better at kind of more nearby sources, or some of them do better for further away sources. And it kind of depends on, in the end, what we found is you kind of make your own priority in terms of what you want to be looking for. Very similarly, we've been looking at if we allow for an arbitrary number of pointings. Of course, you could imagine that at some point this will turn over. You don't want to. You want to take the opportunity to observe more parts of the same part of the sky in order to characterize a potential counterpart than just to point over the whole region. But we've been looking at the efficiency of how many pointings to actually do that for any given telescope. I mentioned this at the beginning, but one thing of particular interest to us at Caltech is how can we actually think about combining the galaxy targeting with this wide field of view telescope work? And so what we've been doing is we've been using that same infrastructure that we developed on the original probability maps, and what we do is we modify them in a small way where we account for galaxy locations and magnitudes. And so what we do is we take our probability map and essentially multiply it by the presence of these galaxies. And so these probability maps become quite speckled. I don't know if you can see it from the crowd, but it's quite speckled here. And we've been exploring if counterparts are actually present in galaxies that we know about, kind of the efficiency improvements we might expect. And depending on what you assume, it can be quite substantial. Finally, we've also been thinking a little bit about how to appropriately schedule multiple telescopes. This is kind of a ridiculous case where we just put a source in the north and a source in the south, and then had telescopes with 2 different fields of view and go after it. But we're also working on how to optimize if you have more than one telescope, which is the case for a handful of teams with very different limiting magnitudes and filters and everything else. How one might appropriately schedule in order to sort of combine their powers instead of schedule completely independently. And I throw this up there just because I worked on Ellis's T for part of my PhD, but a lot of this work, both what we're learning from how to take ZTF, many alerts that ZTF turns out, and how to parse them all in order to figure out which is the one counterpart we care about. ZTF is on a 48-inch telescope, and of course LSST is this 8-meter thing. And so we're just learning how to deal with the sort of rates of alerts that are coming through with ZTF and how to get spectroscopy for the objects that we care about. And of course, this problem becomes almost exponentially harder for LSST. And so ZTF has proven to be kind of a nice stepping stone for thinking about how we might actually do some of this stuff with a telescope like this. Okay, so for the final part of my talk, I'm going to switch back to 1708-17 just for a little bit. And so this is going to get to, we're thinking a little bit about how can we combine the gravitational wave and the electromagnetic observations that we have. And so one of the cool things that came out of 1708-17 was Lena Pien and others had this beautiful, beautiful set of X-shooter spectra, which I probably should have put up here, but I think most people know what I'm talking about. And there were a handful of people, such as Dan Kaysen, who had created models kind of based on 1708-17 and showed that it was able to broadly reproduce some of the features, which was quite nice. And so one of the downsides to how it was analyzed was Dan would take one of his models that seemed to look good, he'd plot it on top and say, well, this one looks pretty good. And so one thing we wanted to do with Dan was to go back and take models like he is producing and potentially like others are producing and say, how can we actually interpolate these models to create posteriors and do what we nominally do in the gravitational wave and do that same thing with the light curves and the spectra that we have. And finally, we can turn around and take those posteriors because they tell us things about how much mass was ejected and how fast it was going and the lanthanide fraction of the counterpart. And turn around and combine it with the gravitational wave measurements to make other kind of constraints you might be interested in. So I'm going to go into a little detail about this, but I'll be reasonably quick. So the way that we chose to do it was actually based on the gravitational wave numerical relativity. It was inspired by that, where in numerical relativity you have all these kind of sparse sampling of parameter space because some of these simulations of binary black holes or binary neutron stars can take months. And so what you'd like to be able to do is say, I have this relatively sparse set of observations or these simulations. How can I interpolate them in order to do parameter estimation? And so we did this in a handful of ways. We computed just the bolometric luminosity as a function of time from the model. Similarly, the magnitude in a handful of bands, or the spectrum. And we used a singular value decomposition to sort of take this matrix of simulations and find the singular values. And then we used Gaussian process to interpolate the values onto the grid of observations. And so what we did essentially is we turned this kind of relatively sparse grid of simulations into a function that we could use to fit the data that we had. So here's an example of two examples of this. So as I said, we did this for the bolometric luminosity. And so I should mention that in the literature for 1708-17, you'll see all sorts of things like 1, 2, 3 component, the blue, red, purple, if you're Edo Burger. But basically, when I say what I mean two component here is where we took one of these models and added it to another version with a different set of parameters. For broadly what we were doing, essentially, you can see the fits here and in this case here. And the fits are pretty good. And essentially, we were kind of reconstructing what other people had been seeing. And so we in the two component case, you have, so this is in log 10 of solar masses, but we essentially showed that by using these fancier models, we were still getting consistency with what was done from before. And predominantly what teams would do before would take black bodies. And so kind of one of the motivations for this analysis was the fact that after 4 or 5 days, the spectra didn't look very black body-like. And so we were quite excited to try non-black body models. But broadly what we were seeing is the when you use fancier models, you get very similar answers. And one thing that was kind of new about this, as far as we knew, is that we were able to do the same thing for the spectra. And so these are the 10 days of spectra that were available. Most of them were from Elena, and then Stephen Smart had a few. But very similar, we were able to reproduce, we were able to interpolate the spectra and do kind of the same measuring of the masses and the velocities as we were able to do in the light curve case. And we saw things like, it broadly fits, perhaps not red enough at the very beginning that you can see up here, but broadly we showed you can successfully interpolate the model and do light curve and spectral fitting. So, as a gravitational wave person, kind of my, one of the motivations for this was, if you just take gravitational waves, there are two things that, there's a handful of things that gravitational waves don't necessarily fit that well, but two key ones are the mass ratio of the objects, as in LIGO measures, or LIGO and Virgo measure chirp masses or total mass essentially quite well, but the mass ratio is not as well measured. Kind of similarly, LIGO does a really good job of putting an upper bound on the tidal deformability of your neutron star. But for example, LIGO has a hard time saying that the tidal deformability is not near to zero. And so the cool thing about these electromagnetic observations is they kind of tell you the opposite, essentially, where due to the fact that you've observed an electromagnetic counterpart, you're assured that you don't have two black holes that are emerging. There's some amount of ejecta that you're getting out. And so what this plot does is it's a 2D posterior for lambda, which is a proxy for how tidally deformable are my neutron stars, as well as Q, which is the mass ratio here. And so we're able together to put a kind of a lower bound on what that might be. And here's a few common equation states people like to quote. Okay, so I'm essentially done, but broadly, if I had to say what the work to do going forward is, the plan is to go back in 01 and 02 and set limits on the handful of other events that we used for that we observed during 01 and 02 with PanSTARRS and Atlas. We'd like to use 1708-17 to inform the tiling strategies that we're doing for existing for the gravitational wave counterpart searches, and we're kind of doing that now. There's still, of course, work to be done on how to actually do the contaminants classifications and probability assessments, but I would like to point out that with ETF, we did observe a very large field of view and had a handful of objects that we're able to classify. Finally, more towards the modeling side, one of the downsides to the analysis that we did with the spectral models was that they were all very symmetric models, and so we would like to explore how to do the same analysis for a non-symmetric simulation, because we expect Kilonovae are not exactly symmetric. And very similarly here, one might think about being able to do inclination measurements if one has a non-symmetric simulation. So these are some of the things we're thinking about. That's what I got.
Thank you very much. We have time for questions. Susanna?
Can you please go back to the plot where you show the afterglow light curves?
And the ZTF sensitivity and time.
Yes.
Yeah, this one. So here you're plotting only short GRB afterglows?
Yes. Yeah.
Okay. And this in hours. Because I was wondering if you were not considering also the possibility to observe a bit later and look for for example, for kind of faint Fermi GRBs, look for the peak of Kilonovae instead, because I don't know if, okay, it's not very likely that you we'll see a short gamma reversed afterglow. Maybe it's not likely, likely as well that you see the Kilonova peak for other cases, but maybe yes.
Absolutely, yes. So broadly, our strategy has been we get an observation or two the first night, depending on how much, where it was. And if we didn't get 2 in the first night, we usually get 1 on the second night.
Okay.
And then when we can, or if we haven't used a bunch of time doing that, depending on the size of the region, we do get 1 about 5 days later. And so that's kind of the amount of time that we have for TOOs with ZTF. So the answer is we'd love to do it, and we're trying to figure out a strategy
cadence,
that minimizes the time while still does it, but it's definitely a balance, yeah.
Okay, thanks.
No.
A short comment and a short question. The comment is about the diagram that you showed very, very early in your talk from the expected number of sources detected. You put your based on the simulation of Metzger and others. They don't usually consider the environment of the source. Therefore, this is, I think it is even more optimistic than what you discussed.
Yes.
Second, for the chance of finding a source, you should only error area around Fermi. However, if the burst is detected with SWIFT, then you have a much better chance. I don't know, have you tried to see in this case how much you have, increased the chance of your detection?
Yeah, so we've internally discussed doing SWIFT triggers, but essentially, what we've settled on together is that if we get an IPN alert that gives some sort of region, we think that ZTF it's worth spending ZTF on a time, because you still have, maybe a handful of degrees in that error box. But for a SWIFT event, that is something that we consciously have left to others, just in terms of not spending TOO time on it. Because as I said, our TOO time is very limited. I expect that with SWIFT, of course, we do quite well, because we cover it, very well. But it was just sort of a decision on our part, because we view it, in addition to sort of looking for afterglows, it's also partially a practice for O3. And so,
do you have a sort of automatic slew to the coordinates?
yeah, so the way that the scheduling and observations are done is we have an automated schedule that's generated, but due to the fact that, again, we have limited time, I still get a phone call and I click a button to decide, are you useful or not. I don't actually know yet. I think it'll depend on how, for example, 3 goes, whether we'll start doing automated observations. It's all technically there. We can do it, but I'm not sure if politically we're going to end up doing that or not. It's not my call to make.
No more questions?
Thanks. So if I understand correctly, you would like to reproduce the same strategy as for gravitational waves detections, which is basically using templates, but for photometry based on Kilonovae models for your research, for your searches of transients with ZTF and also Atlas and also PanSTARRS. And how will you introduce the degeneracy between the masses of the components and the velocity of the ejecta, et cetera, et cetera? How will you tile that parameter space? Will you take inspiration from the way you tile the parameter space for gravitational waves, or?
That's a really nice question. Yeah, so that's not something I've thought a whole lot about. So for the analysis I showed, we were sampling in log 10 of mass space and log 10 of velocity space and log 10 of lanthanide space. And the reason that we thought that was good enough is then we'd remove one of them and reinterpolate and check, do we actually get the right answer? And it seemed to be fine. But I totally agree that more appropriate would be to, we should think harder about how we sample the grid, because especially when we move to a 4D grid where there's yet another variable. So we already had 256 simulations that each took a few weeks to a month to run or something like that. Of course, then adding a factor of 10 will just, kill us. So we should think harder about that, but it's not something we've done.
Okay, then thank you very much again.